Hey everybody, welcome back to my channel. In today's video, we are going to be talking about lesson 10. It is comparing real numbers. This is the last lesson in chapter 1. I hope it's a good one for you. I kind of like it. It's got a lot of terminology. We're going to break it down as best as we can, and then we will see what we can do. So every single number, whether you realize it or not, can be put into a specific category. In this class and in middle school, all of the numbers that you have ever done in your life have been called real numbers. Every single number that you have done so far has been a real number. If you're thinking, is there something called an unreal number? Well, there's something called an imaginary number, and you'll learn about that at high school. But in middle school, everything that we do is a real number. And so now that begs the question, okay, how do we group these into different categories? And so when we talk about real numbers, every single real number can be either rational or irrational. Just like every number can be called even or odd, it's got to be one or the other, right? You will never have a number in this class that is not rational or irrational. It has to be one of the two. And so rational is going to have a whole bunch of different types underneath here. Irrational really only has one type of number, at least in 8th grade. Irrational is very, very unfrequently used in middle school, right? Irrational numbers you really haven't done very much in your life. I bet if I asked you to write down 10 numbers on a piece of paper, almost every single number you would write would be a rational number. So far in all of your schooling, almost every single number you can even think of is a rational number. And irrational really hasn't been a big focus up until, well, maybe this year. So let's start with irrational because it is kind of a smaller group, at least in middle school, that we're familiar with. The only thing that we are going to consider an irrational number is a decimal that never stops and never repeats. Right? The definition of irrational is something you could not write as a ratio of two integers. And we'll talk about more of that in a minute. But in just common sense language, it's a decimal you get on your calculator that fills up the whole screen, that never stops and never repeats. For example, the square root of 7. If I just type this here in my calculator, look what it says. 2.645751311. No repeating. This decimal never stops. It would really go forever and ever and ever. My calculator just runs out of room. Same thing with the square root of 11. Square root of 11, look at that one. Doesn't stop, doesn't repeat, fills up my whole calculator screen. Square root of 50, same thing. If I type that in here, look at that. No repeating bar can be put on here. It goes forever and ever and ever, ever and ever. This is the pi symbol. You might be thinking, well, wait a second. My teacher said the pi symbol is really 3.14. No. I mean, we round it to 3.14, but here's really what pi is, right? 3.15192, right? And it technically goes forever and ever and ever without stopping and repeating. So in 8th grade math, the only thing that you need to remember is irrational are decimals that never stop and never repeat. That's the only thing in this class that will be irrational. Once you get to high school, you may learn some other things. But right now, square roots that are not perfect squares, all right, those square roots that you don't know in your head. I'm not talking about like the square root of 25 that we all know in our head, the square root of 100, the square root of 36, right? Those are going to be over here in the rational group because we actually know those. Those are not decimals. But the square roots that are decimals that fill up your whole calculator and the pi symbol, these are going to be irrational. Irrational. Okay, they don't show up a lot in this class, but they will show up a little bit. Irrational. Now, rational is most of the numbers you've dealt with in your life. Probably 99% of the numbers you've done stuff with in your life have been rational numbers. They are numbers that can be written as a ratio of two integers. And there are kind of 4 little breakdowns here of different types of rational numbers. Just like I could take students and put them into smaller groups, right? We could take Marshall students and we could break them down into like middle school. We could break them down into like 8th graders. We could break them down into what homeroom they're in. We could break them down into, which organization they're in, if they're part of the band, part of the student council, whatever. So we can break rational numbers down just like we can put students in different groups. Oh, these are the students in so-and-so's homeroom. These are the students who are in the orchestra. These are the students who are on the academic team. We can take rational numbers and put them into smaller groups as well. So let's start with the smallest group. The smallest group of rational numbers is this one called the counting numbers. And here I've got a bigger board if you need to see it. Counting numbers is the smallest group you can get. And you're like, what? This is a small group? It actually seems pretty big. Counting numbers start at 1 and they get bigger. Think about a little kid who's playing hide and seek. They go hide behind a tree and they start counting, right? And how do you start counting? 1, 2, 3, 4, right? Blah, 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 blah. Ready or not? Here I come. That type of a deal. Counting numbers are sometimes called natural numbers. Those are kind of synonyms. If you see that, it means the same thing. Counting numbers and natural numbers are the same thing. They start at 1 and they get bigger and they go to infinity and beyond, right? All the way up until you can't count anymore, right? There are no decimals. There are no fractions. There are no negatives. There's not even the number 0 in this. Counting numbers start at 1 and then they get bigger. Natural numbers, counting numbers are the same thing. Okay. The next group right here is called whole numbers. Whole numbers and counting numbers are almost the exact same. Look at the only difference. Whole numbers start at 0 and then they get bigger. 0, 1, 2, 3, 4, 5, 6, blah, 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 blah. So counting numbers and whole numbers are the exact same. The only difference is whole numbers start at 0 and the list we just talked about starts at 1. Right? And so they are very, 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 very similar. There's only one number that's different. Whole numbers, this kind of looks like a hole you've dug into the ground, or you're looking down into a hole, like those manhole covers in the street where the sewer is. So whole numbers start at 0 and then they get bigger. There are no negatives. There are no decimals. There are no fractions. Just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, blah, 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 to infinity and beyond. Okay, the next group is called integers. Some people pronounce that integers because they don't know how to say it. It's integers. Integers, now we're getting even a little bit bigger, right? These include all the whole numbers and their opposites. So like instead of 1, now we also have -1. Instead of 2, we have -2. Instead of 3, we have -3. And so look at these. These are sometimes just a little bit easier to be thought of as just like your number line numbers. If in one of your other grades, your teacher had that number line usually at the top of the wall, right up by the ceiling, and the number line kind of wrapped around the whole classroom. The number line numbers, they have negatives now. We have 0, and then all the counting numbers, all the positives, right? Notice, no decimals, no fractions, but it goes to infinity and beyond this way, and it also goes to infinity and beyond this way. So every single negative number, every single positive number, and the number 0 is included as long as they do not have decimals, they do not have fractions. So like -50, -99, -428, +7, +18, +3,000, +8 million, right? No decimals, no fractions, but we have all the negatives, we have all the positives, and we have 0. Number line numbers, those are integers. Integers, that's a pretty big group. And then finally, there are some numbers that are rational, way down here, you can see at the bottom of my board, that are rational, that just don't fit into any of the categories that we've seen so far, right? Here's what rational numbers are, and now you can see why this is such a big group. Every single number in the counting numbers, every single number in the whole numbers, every single number in the integers, and now we're also going to add percentages. We're going to add terminating decimals. That means decimals that stop, right? 2.7, 5.83, -1.487, right? Decimals that stop, and I forgot on here, and all repeating decimals, and every single fraction, and every single mixed number. Are you serious? Think about that. That's almost every single number you've dealt with in your life. Every counting number, every whole number, every integer, every percentage, every decimal that stops, every decimal that repeats. I didn't write it on here, but that's in there too. Every single fraction and every single mixed number. That's like every single number you've ever done with math in your life. Look at all these. 0. It is a whole number. It is an integer. It's also a rational number, right? -4, 23%, 2 1/5, 0.29, -0.29 with the repeating bar, 3.49, -9 1/6. All of these are rational, right? I could make all of these into fractions if I really wanted to, right? I could make -4 into a fraction of, let me get a marker that's going to work better. These are all rational. We could make all of these into a ratio, right? -4 could be what? -8/2. That's the same thing as -4. 23%, could I make that into 23/100, right? That's a ratio. 2 1/5. If you remember the little trick that you learned, multiply and then add, right? That's the same thing as 11/5. -0.29 with the repeating bar, remember? This is like -29, but instead of saying it's 100 because it's in the 100s place, we say 99 because it has the repeating bar. -29/99. All of these, this is already a decimal. This could be like a 3 and 49 hundredths, right? This could be negative 55 over 6. This could be 0.0158, right? 158 over 10,000. The number 6 I could write as like, what would that be? 60 over 10, or 12 over 2, or 30 over 5, right? This could be negative 10 over 3. If you can write it as a ratio, it is rational. So most everything you've done in your life is a rational number. It's a very, 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 very familiar group to you. Okay, now how are these questions going to be worded? Here's what the questions in the book are going to look like. They're going to say, hey, name all the subsets of real numbers to which these numbers belong. Tell me all the groups that these belong to. Okay, so I'm going to ask myself here, 0.25 with the repeating bar. Is it rational or irrational? It's got to be one or the other. Could I write this as a fraction if I wanted to? Remember, I just did one like it, right? Instead of 25 over 100, because normally you say, oh, that's in the hundreds place. Well, no. These are kind of tricky. Instead of out of 100, since it has the repeating bar, you just take this and lower it by 1, and this is really 25 over 99. So if you can write it as a ratio like this, this is a rational number. Right? It is not, I lost it already, it is not one of these, a decimal that never stops and never repeats. This decimal does repeat, so I can't pick this one because this says never repeats. Excuse me. And this one does repeat, so it is rational. Now, I just need to go through my list. Is it a special rational one called a counting number? No. Do we count 0.25 with the repeating bar? No. If we started at 0 and then went our way up, would we eventually get to this? No. Is this on the number line, 0.25 with the repeating bar, because integers are like our number line numbers? No. So it's just rational. Rational is the only answer for that one. Okay, now we asked this one on our Zoom call, or our Google Meet today, and it was a hard one for people. The square root of 36. Do we know what the square root of 36 is? Of course we do. Isn't that answer 6? So which side should that be on? Is 6 a rational number over here with this category, or is 6 one of these, a decimal that never stops and a decimal that never repeats? The number 6 is not a decimal that never stops and never repeats. Number 6 is over here, right? So the number 6 could be written as a ratio if I wanted to, right? I could call it 12 over 2. So this is definitely rational. But then it's also going to belong to some other of these smaller groups, right? Is the number 6 a counting number? Yeah, look, we could count. If we started at 1 and got bigger, we would eventually get to 10, or get to 6. So it is a counting number or a natural number. Is the number 6 a whole number? If we started at 0 and then went bigger, would we hit 6? Of course we would. So you can see some of these end up in a whole bunch of categories. Is the number 6 an integer? Is it on the number line typically? 3, 4, 5, 6? Yeah, sure it is. And so this number is in all 4 categories. The square root of 36, it is rational. It is a counting number, it is a whole number, and is an integer because it equaled 6. It equaled 6, and that belongs to every single group. Okay, the next one is the square root of 7. Do we know the square root of 7 in our head? I don't think so. So let me type it in here. Square root 7 square root, and then I'm going to make a negative right there. Look what I get. Negative 2.645751311. Which category is that? Is that something we can write as a ratio, or is that a decimal that never stops and a decimal that never repeats? Look at this thing. This is definitely a decimal that never stops and a decimal that never repeats. And so this is irrational. If you pick irrational, you cannot pick anything else. Irrational will always just be by itself. It will never have these others in there with it, because all those others are types of rational numbers. So if you pick irrational, you better not pick anything else. And then this one, negative 2 and 2/5. That's the same thing as negative 12 over 5, right? Remember, you do the multiplying and then the adding thing. Negative 12 over 5, look at that. That is a ratio. It's a ratio of 12 to 5. And so if it's a ratio, we're going to pick rational. And then let's check these smaller groups. When I count, if I start at 1 and I get bigger, will I eventually get negative 2? No. Negatives aren't a member of counting numbers. Are negatives in whole numbers? No. Are negatives in integers? They are, but are negative fractions? No, look at these. None of these have fractions or decimals. And so this is just rational. It's just like letter A. It does not have any of the other categories. Okay, let's try another type of question. They'll also ask you like this. They'll say, okay, guys, now do less than, greater than, or equal to. Okay, that doesn't seem too hard. Don't try to do these in your head. Use a calculator. Use the calculator on your phone. Use the calculator on your computer. Use the calculator. That's an actual calculator, right? Square root of 7. If you can't figure out how to find it, type it in Google. What is the square root of 7, right? You can find it. 7, shift, square root. There it is. 2.645751311. Now, I'm not going to write all those numbers. How about I just write a couple? 2.645. How about that? And now this one, 2 2/3. We did this way back at the beginning of the chapter. I know this is going to be 2 point something because it starts with a big 2. Now I just need to do 2 divided by 3, right? A fraction is a way of showing division. So 2 divided by 3 is 0.6 with a repeating bar. So I don't need to put all those. I'm just going to put a couple. And now you can tell which one's bigger. Is 2 and 2.645 or 2.666 bigger? And obviously this is bigger because it's 66 and this is only 64. So this one is larger. That is the less than symbol. On letter F, same idea. They gave you a percentage. Don't let that bother you. I hope you remember from 7th grade how you make a percentage into a decimal. You move the decimal 2 places to the left, and look what I get, 0.157. And now 0.02 with a square root around it. I don't know that in my head. You don't know that in your head, and that's okay. That's why we have calculators. Look what it is. 0.141421356. And really it goes for more than that. We just ran out of room. I'm just going to put 141. Now is it easy to tell which one's bigger? 157 or 141? Easy, right? 15 is bigger than 14. And so this has got to be greater than. And then down here, 6.2 with a square root. I have no idea what that is, but that's fine because I have a calculator. 6.2 square root, look what I get. 2.489997. Blah, blah, blah. I'm just going to put 2.48. 2.48. And then now look at this one, 2.4 with a repeating bar. Isn't that just going to be 2.44444444 forever? So what's bigger, 248 or 244? Obviously 48 is more than 44, and so we want to go with 48 on this one, greater than. These questions are easy. Use your calculator. Use it on your phone. Use a calculator if you have a real calculator. Use a calculator on the internet. You can find a calculator, hopefully somewhere, to help you. Your computer probably has a calculator on it as well. Okay, the last one, and then I promise I am done. What if they want you to put the numbers in order from least to greatest? It's kind of hard when they all look like this and they're all different. Make them all decimals, and then it's easy, just like we did on those last ones. Convert everything to decimals, and then it's a lot easier to compare. So the square root of 30, do I know that? Nope. But does my calculator know it? You sure bet it does. Look at that, 5.477. I'm just going to say 5.47, and then if I need to put more in there, I will. So this is like 5.47. Okay, the number 6, I don't really need a calculator for that. That's just like what, $6? Like you see something at a store that looks like that at $6. 5 4/5. I know it's got to be 5 point something because it has a big 5 on it. What is 4/5? I'm going to do 4 divided by, whoops, I hit times, clear that out. 4 divided by 5, and you get 0.8. So instead of 0.8, this is 5.8. I'm going to put a 0 on there so it kind of looks like a money amount like all these others. And then 5.36, the 6 is repeating, but I don't really need that third decimal right now. It's a lot easier to tell which one is least to greatest now, right? If you had to put this on a number line, could we do like, let's just say 5.3, 5.4, 5.5, 5.6, 5.7, 5.8, 5.9, and then 6.0. Like we could put all these on there. That wouldn't be too hard. It's pretty easy to tell the list, right? The smallest one, least to greatest. The smallest one is going to be this one, right? $5.36. Whenever you go least to greatest, or whenever they give you a list, you better use the real, don't use the decimal, use the actual one they used in the list. So I'm going to say 5.36 with the repeating bar is the smallest. That one's first, and that on a number line would be like right here, 5.36, the repeating bar. And then what's next? 547 is smaller than 580. So then the square root of 30 Square root of 30 is next. 5.47 is like almost 5.5. So I'm going to put square root of 30 right there. Sorry about that. Not looking very neat. That's just 30. And then 5.8, which is 5 4/5 right here. 5 4/5. That's going to be third in my list. And then finally the number 6, which is just going to be right there. And it's just a 6. So you can see I took the list and I put it in order using the original numbers. Don't use the little decimals you made to help yourself. Use the actual numbers they wrote in the question. And then I was able to put it on a number line. And there you go. That looks a little bit better, like a 30 now. Okay, I'm going to stop this right here. I hope that gives you a good explanation. Feel free to pause this video, rewind it. I'm going to put some questions on the McGraw-Hill site, and I hope that you are able to do them. If not, ask me some questions, and we will be more than happy to help you out. Okay, have a good one, guys.